to the culmination of Darwin Week 2012. Let me adjust the microphone. My name's Corey, and I'm the president of Unify. A few quick things before we get started. I have a list. First, you'll see on your chair, those of you that have a chair, we have these speaker rating forms. Please fill those out. It helps us out a lot. We want to make sure that we are doing all we can to make Darwin Week really awesome, and you can help us out by filling these out. Also, after the talk, there will be book signing in the lobby right over here. There are several books for sale. They're all, I'm sure, amazing, and one of them is I guess, the theme of tonight, The Universe from Nothing. Now, sorry, one final thing. You'll notice that there are a lot of people wearing these really cool shirts. They might have a Unify logo on the front. They might say Darwin Week on the front. Joe's standing back there looking really smart in his Unify shirt, or his Darwin Week shirt. We have shirts for sale outside of the CME lobby. The Darwin Week shirts are $5. Unify shirts are $10. So that is that. Our next speaker, I guess in introducing Lawrence Krauss, I could say a bunch of things. I could read off from the bookmark. There's certainly a bunch of great stuff on here. He's the director of the Origins Project at Arizona State University, an advocate of scientific skepticism, science education, and the science of morality. And that's all well and fine. I could talk about Dr. Krauss's published works, including A Universe from Nothing, Quantum Man, a biography of Richard Feynman, and The Physics of Star Trek. But I wanted to talk a little bit about the significance of this talk to me. I have a friend who will remain anonymous, and he's religious, and he's really stuck on this idea that this question of how there could be all this nothing, or I guess all of this nothing isn't even, there can't be all of this nothing, just nothing, and then suddenly all of this something, and how this must have there must be some kind of a creative genius behind this. And many apologists are stuck on the same thing. They say, one of the most important questions you could ask an atheist is, why is there something rather than nothing? So I think we have the best person in the world here to answer that question, and to explain to us all why my good friend is mistaken. So please join me in welcoming Dr. Lawrence Krauss to Darwin Week 2012.
Let's get rid of this. Okay, good. Hi, thank you very much for coming on such a beautiful evening. Apparently. I just came from Phoenix, but anyway. It's very, very nice that it's not snowing. And I'm very pleased that you all came out. And I wanted to indeed address a question which is fundamental and has been around for as long as people have been around, and as was pointed out, is perhaps the last bastion of theology. I've often encountered it over the years when people ask me, why there's something rather than nothing. So, by the way, these are stars. I used to live in Cleveland, and I used to have to tell people, these are stars. In Phoenix, they can see them, but you can see them out here at night. But so this question has a lot of answers. What I want to point out is that it's very different than it was before. That in fact, this question is not a theological or philosophical question, thank goodness. It's a scientific question, because something and nothing are scientific quantities, they're physical quantities. We have to understand them as physical quantities, and science has completely changed our understanding of them, as I want to talk to you about it. I want to celebrate that change, and in the process, point out some remarkable things that we've learned about the universe. Now, there's a lot of ways to answer this question. The first way is a simple way. You can say this: in the beginning. But that doesn't do anything. That doesn't answer anything, doesn't explain anything, doesn't lead to any knowledge whatsoever. That's an explanation based on invented answers and myths by people who didn't even know the earth went around the sun. And what I want to do is try and answer the question as we understand it now, and that means going back to the universe, getting our answers. In fact, one thing I wish I could really explain to people is that, and I'll keep repeating it, is that the universe is the way it is whether we like it or not. And if we want to learn about the universe, we have to get the universe to answer our questions. We can't impose what we like upon the universe because it doesn't really care. And so one of the remarkable things that led me to write this last book was the discovery that this is a globular cluster in the night sky. If you look at it with a telescope, you'll see this beautiful star cluster. And it's beautiful. The stars are beautiful at night, far away from the city. But what we discovered is that the really important... Does this thing keep going off and on? I didn't do anything. Okay, well, off screen. Okay. Does that work yet? No? I notice it's still got a light on it. But you can play. I'll screen it. Good man. I'd rather not use the microphone anyway, but, well, I mean, if it works, I'll... Can you all hear me okay?
Yes.
Okay. If you can't, you're not missing anything. Anyway, so the really important stuff is not the stars, but the stuff between the stars. It's changed everything about the way we think about the origin of the universe and its future, as I'll try and describe. So, the way I want to begin this mystery story, which it really is as all good mystery stories should begin. It was a dark and stormy night. I refer not, of course, to the origin of the universe, but rather to the night that Albert Einstein dotted the last period on his equations of general relativity in 1916. It was his greatest triumph. It was the first theory that was not just a theory of how things move through space and time, but how space and time themselves evolve. And it was a remarkable theory because it said space is dynamical. It can respond to the presence of matter. And because it was a theory of space and time, it was the first theory that could be a theory of the universe. And he was incredibly excited about that. And he knew it was the correct theory. He was convinced by a number of things. But there was a problem. It didn't describe the universe in which he lived. Nowadays, that doesn't bother physicists so much, but it used to. And he was really concerned about this fact. And the real problem was a problem that should be familiar to all of you who've taken physics, which is all of you, I hope. Gravity sucks. It always pulls, it never pushes. And that's true for Newtonian gravity, but it's also true for general relativity. And in 1916, less than a human lifetime ago, really, for long-lived humans, the universe was static and eternal. That was the conventional scientific wisdom, that the universe had been around forever and would be around forever in exactly the same form. And the problem is you can't have a universe that's static and eternal if gravity sucks. Because you put stars out there and they always collapse together. And so Einstein was very discouraged by that, but then he was a very creative guy, and he realized he could modify his equations. And so I want to show you this. So I want to write down Einstein's equations here. I've asked the doors to be locked. So there's no getting out of this now. Okay, this is Einstein's. This is for biologists. Don't pick on philosophers. This is for philosophers. Anyway, it's not completely facetious, but I hope you're all with me. The left-hand side equals the right-hand side. We're okay with that? Now, it's not facetious completely because, in fact, in Einstein's equations, the left-hand side of the equation relates to the fact that space can curve in the presence of matter, and it describes the geometry of space. And the right-hand side is the stuff that makes space curve, which is the energy and momentum of stuff in the universe. And that's the physical content of Einstein's equation. Stuff causes space to curve, which affects the properties of stuff. And I'm a theoretical physicist, so I have to write down the Greek letters, and that's much more illuminating. So this is the equation that had problems. And Einstein realized that consistent with the mathematics, the symmetries that had led him to develop general relativity, he could modify this equation slightly by adding a new term on the left-hand side. And that term he called the cosmological term. And what he realized that this would do was that this would produce a small repulsive force throughout all of empty space. So small that you'd never measure it here on Earth. It wouldn't destroy the beautiful calculations of Newton that had led to his universal law of gravity in the solar system. It would be imperceptibly small. But on the scale of the universe, of the galaxy, it could build up and it can hold distant stars apart. So we thought this would be the solution. Now, almost immediately after we wrote down this, problems started to arise, and in fact, when I was in Switzerland a few years ago on leave, I got this postcard from Einstein to Hermann Weyl, who's a very famous mathematical physicist, from 1923, and it said, some of your German is probably better than mine, but if you get rid of a quasi-static universe, then out with the cosmological constant, out with the cosmological term. Because already by 1923, it was beginning to be understood that the universe wasn't static. And he realized if the universe is expanding, you don't need this cockamamie cosmological term anymore, because gravity can suck. Because if the universe is expanding, gravity can work to slow the expansion, and the big question of 20th century physics, the holy grail of cosmology, became, is there enough gravity to stop that expansion and reverse the Big Bang expansion, reverse the Big Bang, the big crunch, or will the universe go on expanding forever? That became the big issue. And so he called the cosmological term his biggest blunder. He wished he'd never included it. Now, while there were inklings in the 20s that the universe wasn't static, the person who convinced the world that the universe isn't static is one of my heroes, this guy right here, Edwin Hubble. He's a hero of mine because he gives me great faith in humanity. Because he began life as a lawyer and then became an astronomer. So there's hope for even some of you. And Hubble did many things. With the Mount Wilson telescope, he actually made a remarkable discovery, somewhat peripheral to what I thought is probably worth mentioning, because it gives you a sense of how new our understanding of the universe is. In 1925, not only was the universe static, but we knew our universe consisted of the Milky Way. One galaxy. That was the universe. If you looked at our Milky Way galaxy with telescopes available up to that time, you just saw the Milky Way. You saw these fuzzy things in the Milky Way when you looked, and they were called nebulae, and that's Greek for fuzzy thing. And there was a big debate about what they were. And with the Mount Wilson telescope in 1925 looked strong enough for Hubble to conclusively prove that these nebulae were in fact other island universes, other galaxies. We now know that there are 400 billion galaxies in the observable universe. And until 1925, we knew of one of them. So in 87 years or so, everything has changed. So you understand, we're like the early map makers. We're just beginning to understand the universe on larger scales. So it's not surprising that we're often surprised. And I want to relate to you those surprises because they have profound implications, not just for understanding the universe, but perhaps for understanding where we came from. Okay, so Hubble was the one who discovered the universe was expanding, and this is how. Okay, these are galaxies, not sperm. That was for you had that a different day, I think. So we are here, and what Hubble discovered is that as you look out, as he looked out at other galaxies, all the galaxies on average are moving away from us. And those that were twice as far away from us are moving twice as fast. Those who were 3 times as far away from us are moving 3 times as fast, and so on. So what does this tell you? Well, it's obvious. It tells you we are the center of the universe. That's not true. As some of my friends remind me on a daily basis, it's not true. It's not. The reason it looks like we're the center is that we have this myopic. We're stuck in our universe. Most of us are stuck in our universe. Well, except the Republican candidates, but everyone else in our universe. And that's the problem. So if you want to see the universe expanding, we've got to get outside our universe. Well, it's hard to do it in the real universe, but I can do it in a fake universe. I can create a 2-dimensional universe. And then I can put galaxies on a regular grid here, and you can see that at one time, T1, the galaxies are this far apart, and then this region of the universe has grown. At T2, it's bigger. So if you're standing outside, you can easily see that the universe is expanded. But what would you see if you were living in this universe? Well, pick a galaxy, any galaxy, say this one. And what I want to do is put it on top of itself, superimpose this image on top of this one, putting this galaxy on top of itself, and ask what you'd see from that galaxy. And you see exactly what Hubble saw. Every galaxy is moving away from you, and those that are twice as far away move twice the distance at the same time. Those that are 3 times as far away move 3 times the distance. And it doesn't matter what galaxy you pick. Any galaxy, you see exactly the same thing. So, depending upon your mood, either every place is the center of the universe, or no place is the center of the universe. It doesn't matter. What this is telling us is that the universe is expanding. And of course, that was profoundly important because if the universe is expanding, it had a beginning. And that changed everything, and not just science, but theology. Because it meant the universe did have a beginning. It turns out the beginning is 13.7 billion years ago, not 6,000, except in Ohio and Arkansas and a few other places. But it meant the universe had a beginning. Now that, as I say, that was profoundly important, and I want to explain, this is such an important observation, I want to explain how Hubble got it. So, he's measuring the velocity of galaxies away from us as a function of their distance. Those that are farther away are moving faster. So what does that mean? Well, you've got to measure velocity, and you've got to measure distance, if you want to find that relationship. So velocity is easy. These two cowboys on the plane looking at this train know all about this. One says to the other, I love hearing that lonesome wail of the train whistle as the magnitude of the frequency of the wave changes due to the Doppler. What they are reminded of is a very famous fact that as the train is coming towards you, the whistle sounds higher because the sound waves get scrunched up. And as the train is moving away from you, the sound waves get stretched out, it sounds lower. And the same thing happens to light, but for different reasons. And that means when we look at stars, if they're moving away from us, the light is stretched out compared to the frequencies with which that light was emitted. And the long wavelength radiation in the visible end of the spectrum is the red end of the spectrum, so the stars look redder. If they're coming towards us, they look bluer. And so what Hubble discovered is that the stars and galaxies that are further away from us are progressively redder. They have a bigger redshift, as it's called. So the velocity is the easy part. You just measure the frequency of light emitted by the galaxies, you see how much is shifted, and you know their velocity. But the hard part is distance. How do you know farther away galaxies are farther away? Well, that's hard because we don't have tape measures that are that long. So you got to think of some way to measure distance, and of course use the laws of physics. So I can tell the distance to the back of the room if I turned on all the lights except for one of the lights in the back, and I say it was a 100-watt light bulb. And all of you almost are too young to remember the days when cameras had light meters, but they used to. And if I knew there was a 100-watt light bulb there and I had a camera right here with a light meter and it told me there was 1 watt of light coming into my camera, I know how the light spreads out. I know it's 100 watts there, and 1 watt here, I can figure out how far away it is. So that'd be great if the universe were populated with 100-watt light bulbs, but it's not, unfortunately. So we have to look for the equivalent, something called a standard candle, something whose intrinsic brightness we understand. And then we look at it through a telescope, see how bright it looks, and then we know how far away it is. Okay? So that's been the hard part, because it's hard to find standard candles. And that's one of the reasons, this is Hubble's original data from 1929. Velocity versus distance. And this is one of the reasons he was such a great scientist. He knew to draw a straight line through that data set. It's not at all obvious. Just a lucky guess, in fact. But he did something else that was profoundly important for us. He got the answer wrong by a factor of 10. And most observational astrophysicists have tried to continue that tradition. It actually was very embarrassing because he discovered the universe was expanding 10 times faster than it actually is. And if you work enough, you know how fast the universe is expanding, you can figure out how old it is because you can figure out how long it took things to get out to where they are. And if this were true, the age of the universe would be 1.5 billion years old. But people already knew in 1929 that the Earth was older than 1.5 billion years old, except in Arkansas and Ohio and a few other places. So it was a little embarrassing when the Earth was older than the universe. Something we didn't like to talk about. But happily, he got it wrong. And he got it wrong not because he was a crummy astronomer, but it's very difficult to find standard candles. We now know the expansion rate is almost a factor of 10 lower. And so the universe is almost 15 billion years old, 13.7 billion years old. And we've been able to do it because we have new kinds of standard candles. And here's the best standard candle we have. This is a Hubble Space Telescope picture, one of my favorites, but then they're all my favorites, actually. This is a galaxy long, long ago and far, far away. It's actually not that long ago and that far away. It's only 50 million light years away. So the light from this galaxy was emitted 50 million years ago. And before it was received by the camera that took this picture. It's a spiral galaxy, just like our own. You've seen one, you've seen them all, more or less. And there's something interesting about this picture. In the center of the galaxy, this galaxy, like almost all galaxies, contains about 100 billion stars. And the center of the galaxy contains about 10 billion stars. But here's a star that's shining with the brightness of the whole center of that galaxy. How could that be? Well, the first thing to assume is that it's a star in our galaxy that got in the way of the picture. That's a reasonable assumption. It's wrong, but it's a reasonable assumption. It is, in fact, a star on the edge of that galaxy. And it is, in fact, shining with the brightness of 10 billion stars. How can that be? Well, it's a star that's just exploded. A supernova. The brightest fireworks in the universe. When a star explodes, it shines briefly, a period of about a month, with the brightness of 10 billion stars. Now, fortunately for us, stars don't explode too often. But fortunately for us, they explode, because we wouldn't be here otherwise. Stars explode about once per 100 years per galaxy. Now, the reason it's fortunate is that every atom in your body essentially came from a star that exploded. Because the elements that were created in the beginning of the universe, in the first second or minute or so of the Big Bang, were just hydrogen, helium, and a little bit of lithium. Okay, but the stuff that's important for you, well, some of you may depend on lithium, but the rest of you, carbon, nitrogen, oxygen, all the things that we depend upon weren't created in the Big Bang. They were created in the nuclear furnaces and the cores of stars. And the only way they could get into your body is if the stars were kind enough to explode. And over the course of the lifetime of the Milky Way galaxy, 200 million stars have exploded. And there are atoms in your left hand that have come from different stars in your right hand. So, Alex, stand up. I'm going to read it because I don't want to say it. It says, it really is the most poetic thing I know about physics. You're all stardust. You couldn't be here if stars hadn't exploded. So forget Jesus, the stars died so you'd be here today. I said that in a lecture once, and it's become like a bumper sticker, and now it's on T-shirts. But it really is the most poetic thing I know about the universe. You are stardust. Think about that. Every atom in your body has experienced the most violent explosion in nature. Maybe more than once. Probably more than once. So it's remarkable. But in fact, in any case, these supernovae are standard candles because this type of supernova, called the Type 1a supernova, for reasons I don't have time to go into, we think we understand its intrinsic brightness. And if we can study these things, and the galaxies are in, we can measure how far away the galaxies are and determine the Hubble expansion. But how can you, if these stars explode once per 100 years per galaxy, how can you study them? Well, simple. You assign a graduate student to each galaxy. 100 years is about the right time for a PhD. Graduate students are cheap. If they die, you just get new ones. But we don't have to do that because the universe is big and old. That's the other amazing thing about the universe. And rare events happen all the time. So if you go out tonight and it'll be dark here and you'll be able to see the stars. It's a clear night. Take your arm and hold it out and hold a dime-sized hole and point it at a dark spot in the sky where there are no stars. With one of the biggest telescopes on Earth today, if we looked at that dime-sized region, we would see about 100,000 galaxies. Now think about it. Once per 100 years per galaxy, 100,000 galaxies. On a given night, you'll see one or two stars explode. Statistically. And astronomers do that. They apply for telescope time. They say, tonight I'm going to see a few stars explode, and they do, unless it's cloudy. So we can take movies of stars exploding, because we can look at 100,000 galaxies in a single image, and we can see these stars get brighter over the course of a day or two, and over the course of a month, and we can and here's this movie that shows this star explode and its brightness over the course of time, and more important, its colors, because that tells us it's a specific type of supernova, Type 1a supernova, which is a standard candle, and allows us to measure the expansion rate of the universe. It's so important that this year's Nobel Prize in Physics, in fact, as I'll describe, went to people who used these objects to measure what was happening to the universe. So now we have a much better Hubble picture than Mr. Hubble did. Here it is. It's, of course, was made after the important fundamental realization that on a log-log plot, everything is a straight line. But in spite of the guide to the eye, we can now measure the Hubble expansion rate to not a factor of 10 uncertainty, but to 10% uncertainty. So we know how fast the universe is expanding. And then we can begin to ask the question, what will happen in the future? In fact, the reason I got into cosmology is I wanted to be the first person to know how the universe would end. It seemed like a good idea at the time. So the reason is that, okay, Einstein tells us that space is curved. Now, I can't draw curved three-dimensional universes, and you can't picture them, because we're three-dimensional beings. But I can draw curved two-dimensional surfaces, so these are analogies to curved universes. And it turns out, because space can be curved, it can exist in one of three different types of geometries, the so-called open, closed, or flat. And so, I can picture them here. Here's an open two-dimensional universe, a closed surface of a two-dimensional sphere is a closed universe, and a flat universe is like a flat piece of paper in 2 dimensions. I can't picture it in 3 dimensions, but I can tell you, for example, in a closed universe, if we lived in a closed 3-dimensional universe, if you looked far enough in that direction, you would see the back of your head, as light would go around the universe. Space would close on itself. And that sounds great at cocktail parties or try-test people in bars or whatever, but what's really important is that in a matter-dominated universe, if the universe is closed, it will expand, stop, and recontract. An open universe will expand forever, and a flat universe is the boundary between the two, slowing down and stopping. And that's why I got into cosmology, because I figured if I could determine which universe we live in, I could determine the future. We know how fast the universe is expanding, and to determine which universe we live in, the only other thing we have to do is weigh the universe. And it turns out that's easy. Well, it took 80 years. But there's a lot of, I actually wrote a whole book about it once, but in fact we can now weigh the universe using a simple idea that was first proposed, it turns out in 1936 in this paper in Science, one of the preeminent science journal. I want to take you back here because you're all young and some of you may become scientists, and I want to remind you of a kinder, gentler time. And so in 1936, this paper was written, and it was called Lens-like Action of a Star by the Deviation of Light in the Gravitational Field. And here's how the paper began. Some time ago, R.W. Mandel paid me a visit and asked me to publish the results of a little calculation which I had made at his request. This note complies with his wish. Now try to submit something like that now. Now, it turned out the author had credentials. The author was Albert Einstein, so they But what he presented was a calculation they thought was completely irrelevant. He had realized, he knew that light curved in a gravitational field. That was one of the predictions of general relativity, verified in 1919, that made him famous. But therefore he realized if you have a big enough mass, and you have a light source behind the mass, the light rays can go around it and come back and converge and be magnified, like my glasses magnify nearby objects. Or if I had a cut glass goblet, I'd see many images of you if I held it up. And he realized that space could do that. But he said the effect was so small it'd never be observable. So here were the notes. Here was the calculation that Mr. Mandel asked him to publish. And in fact, he thought it was so unimportant that he actually had forgotten. This is from 1936. If you look at his notebooks from 1912, he did exactly the same calculation. He'd forgotten he'd done it. Because he thought it was unimportant. And it's actually kind of fun if you read the letter he wrote to the editor afterwards. He said, "Let me thank you for your cooperation with the little publication which Mr. Mandel squeezed out of me. It is of little value, but it makes the poor guy happy." That's how science is done. Anyway, it turned out to be not of little value because it allows us to weigh the universe. And in fact, here's a picture of the phenomena that Einstein said we'd never see. This is another Hubble Space Telescope picture. And one of the amazing things about this picture is every spot in this picture is not a star, it's a galaxy. Every one of these galaxies contains hundreds of billions of stars. This is a cluster of galaxies. The biggest bound objects in the universe are clusters of galaxies. 10 billion light years across. Our galaxy is in a cluster of galaxies. This particular cluster is located 5 billion light years away. That means the light left these stars 5 billion years ago, before our Earth and Sun formed. Got here. Most of the stars in this picture don't exist anymore. They're burned out. And it is amazing to think about the civilizations that had once existed on these galaxies that are now long gone. I find it poetic to look at a picture like this as well. But in spite of that, I want to talk about other stuff. But it's amazing that we can take such pictures and see the universe as it is. But you don't have to be a rocket scientist to see in this picture that there are these weird blue things, and they are very different than everything else. And what those things are multiple images of a single galaxy located 5 billion light years behind that cluster. And that galaxy, the light from that galaxy is magnified and distorted So you see many different images of it, but they're all images of the same object. This is the curvature of space for real. This is a gravitational lens. And it's profoundly fascinating to look at, but now we understand general relativity, so we can work backwards. We can ask how much mass must there be in this system, and where is it distributed in order to create this image, just as we could do for a glass lens. And we do that, we find the following picture. This is where the mass is in that picture. The spikes are where the galaxies are. But you notice that most of the mass in this cluster is where the galaxies aren't. This mountain of mass is where the galaxies aren't, in the darkness between the galaxies. And we know that 40 times as much mass exists in this system as meets the eye. And the same is true for all clusters. And physicists, because we're so linguistically challenged, call this stuff dark matter, because it doesn't shine. But we have discovered that at least 90% of the mass of the universe is dark. And moreover, there's so much of it that we're now convinced, for reasons I again won't go into here, that there's too much of it to be made of normal stuff like you and me. It can't be made of the same elementary particles that make you and me up. There aren't enough of them. So we think it's made of some new type of elementary particle, which makes it quite exciting, because that doesn't mean it's just out there. It's in this room. It's going right through your bodies as you doze off during this lecture. And that means we can do experiments here on Earth to detect it. We can build detectors deep underground. We put them deep underground because cosmic rays are bombarding us all the time. We want to go away from these things. And these elementary particles we think interact so weakly, most of them go right through the Earth without knowing it was there. But every now and then they'll bounce off, we hope, a detector. And I'm very pleased that one of the things I did about 25 years ago was propose the detectors that are now being built for this stuff. And then maybe give a signal of this dominant stuff in the universe. Now, it turns out there's a race, because this dark matter we think was created almost at the beginning of time and been around since then. So we're either looking for this signal from the beginning of time, or the other place we can look for it is a place that recreates the earliest moments of the Big Bang. Such a place exists in Geneva, Switzerland, or near it, the Large Hadron Collider, the biggest accelerator in the world, where over a very small region we create those kind of conditions. And so there's a race on between the people building direct detectors and the people who are looking for the products coming out of the collisions in Geneva, and we don't know where we'll discover dark matter, but if we do, we'll discover the identity of most of the mass in the universe. Now it turned out because of this, and because these are the heaviest bound objects in the universe, if you can weigh these things, you've weighed the universe, because anything that can fall into anything will fall into a cluster. So before I give you the answer, I want to just step back and tell you the first lesson I want you to take from the lecture is you are much more insignificant than you thought. You can take us and everything we see, and we're just a small bit of cosmic pollution. Get rid of all the stars, everything that's beautiful in the night sky, and the universe would be largely the same. So much for a universe made for us. We're a sideshow. The real stuff is dark matter, and you'll see the real stuff is even more exotic still. But we can weigh the universe, and finally, the Holy Grail. Ta-da! I see gasps. I hear gasps. Fainting in the back of the room. Well, in physics, whenever we get an important number, we give it a Greek letter, so we sound scholarly. We call it omega. And omega is the ratio of the total amount of stuff, matter in the universe, divided by the amount of matter you would need to make an exactly flat universe. So if omega is less than 1, the universe is open. If omega is greater than 1, the universe is closed. And if it's equal to 1, the universe is flat. And we now seem to discover with huge accuracy that the universe is open. And therefore, the Holy Grail of cosmology is satisfied. We live in an open universe, expand forever. Well, there's a problem with this. We theorists, we knew the answer. We always know the answer. We're usually not right, but we always know the answer. And we knew that we live in a flat universe, because a flat universe is the only mathematically beautiful universe, for reasons I'll describe. And here these damn observers were getting the wrong answer. Well, they always get the wrong answer. But it's a problem. Well, there's a it's not too much of a problem, because you see, you're weighing stuff. You're measuring the expansion of the universe. You're weighing the mass of these things. You're plugging it into Einstein's equations, working backwards, trying to determine the curvature of the universe. Wouldn't it be better to measure the geometry of the universe directly? Of course. And the answer is yes. And in the last decade or so, we've been able to do that, which is remarkable. I never would have believed we could do it. Actually, after we did it, I remember I wrote a paper 20 years ago talking about how we could do it, but I'd forgotten. So let me ask a simpler question. How can you measure the curvature of the Earth if you couldn't go outside space and see that it was curved, or you couldn't go around it? You were here in Iowa and it looks flat. Okay? Well, very simple. You draw a triangle. You'd ask a European high school student, what are the sum of the angles in a triangle? And 180 degrees. And then you'd say, no, that's fine. You learned your geometry from Euclid. But in a curved surface, it can be different. You take the Earth, you can draw a straight line along the equator, make a 90-degree angle to the North Pole, make another 90-degree angle from the North Pole. You got a triangle with three 90-degree angles. 3 times 90 is 270. And therefore, you would know the Earth is curved. So, to know the Earth is curved, you just draw a big enough triangle, and you see a deviation from 180 degrees. Now, that's true for a two-dimensional surface, but it turns out in this case, it's also true for a three-dimensional space. If a three-dimensional space is curved, if we get a triangle that's big enough, and the angles don't add up to 180 degrees, we've measured the curvature of the universe. And in the last decade or so, we've been able to find a triangle that's big enough. And it comes from one of the most important observations in cosmology, the cosmic microwave background radiation, the afterglow of the Big Bang. Radiation coming at us from the Big Bang. The few people who are my age in the audience have seen it. None of the rest of you have, because you grew up with cable TV. But in the old days, TV stations used to go off the air. And after a while, there was a test pattern, and then there'd be static. And 1% of the static on your TV screen, if you disconnect your cable, God forbid, is radiation from the Big Bang. So next time you look at that static, and I won't say what you're doing at the same time as you look at the static, but anyway, think it's 1% of it is coming from the Big Bang. Now, even though it's there and so obvious, we didn't even know it existed until 1965. It was discovered in 1965 in New Jersey, of all places, by two people who didn't know what the hell they were doing. but they won the Nobel Prize anyway. Because you don't have to know what you're doing to win the Nobel Prize. You just have to. You don't. No, seriously. You don't. You just have to make a big discovery. You don't have to. And that's perfectly reasonable. You have to change our understanding of the world. You didn't have to know you were going to do it beforehand. And that's often the case, as you'll see. In fact, there's another example I'll talk about. But let me tell you where the cosmic microwave background comes from. As we look out here from the Earth, 10 billion years old, when we look at galaxies that are a billion light years away, well, we're looking back in time. We're doing cosmic archaeology, as I told you. And now you think about it, if the universe is 13.7 billion years old, if you look back far enough, you should see the Big Bang. Well, that's true in principle, but we can't see all the way back to the Big Bang because between the Big Bang and us is a wall. Not a physical wall like this, but essentially one. A metaphorical wall. I can't see past this wall because that covering there is opaque. And if I look out at the universe at earlier and earlier times, it was hotter and hotter and hotter. And when the universe was 100,000 years old, it had a temperature of 3,000 degrees. At that temperature, hydrogen, which is the dominant stuff in the universe, gets broken apart by radiation into protons and electrons. And instead of neutral matter, you have what's called a plasma. And a plasma is opaque to radiation. You can't see through it. Before this time, the universe is opaque. So let's run the film forward. You got this opaque universe, opaque. Then suddenly, it cools down to 3,000 degrees. Suddenly, hydrogen, protons can capture electrons. Matter becomes neutral, and neutral matter is transparent. So just like I can see that wall, because my laser beam bounces off the wall, comes back, bounces off that surface, and the air between me and the wall is transparent, I can see that wall. If I look out here, I should see radiation coming at me from all directions at the moment the universe became transparent. And the prediction of the Big Bang, one of the predictions is that such radiation should exist. And of course, the universe is cooled between then and now, and we should therefore see not 3,000 degree radiation, but about 3 degree radiation. And that's what those bozos in New Jersey discovered. By accident. Now, it's profoundly important. It was worth the Nobel Prize because it told us the Big Bang really happened. This is radiation coming from the Big Bang. Now, on this, if we could image this surface, if we could take a picture, then we'd see what the universe looked like 13.7 billion years ago. We could get a baby picture of the universe, and I'll show it to you in a second. But on that picture, there's one important scale. It's 1 degree across. Why 1 degree? Well, this distance is 100,000 light years across. And if the universe is 100,000 years old, Einstein tells us that no signal can travel faster than light. No information can propagate faster than light. And therefore, if this universe is 100,000 years old and this is 100,000 light years, this is how far a light ray could travel in that time. And that means nothing over here could affect anything over here. And that means if you have a lump of matter, well, it starts to collapse because of gravity and it heats up and all these things happen if it's this big. But if you have a lump that's this big across, it doesn't even know it's a lump because gravity hasn't been able to travel across it in the history of the universe. So it's like Wile E. Coyote. You remember when he runs off his net, he just sort of sits there for a while before he realizes it's supposed to fall. And that's the way it is. These big lumps won't collapse. The biggest lumps that could have collapsed are 1 degree across. But that gives us a triangle. Because there's a triangle with on one side 100,000 light years across, a known distance away from us, and in a flat universe, light rays travel in straight lines, and that 100,000 light year across ruler will span a size of 1 degree on our eyes. But in an open universe, it turns out light rays diverge as you go back in time, and that means that same ruler will look smaller. That same lump with a fixed physical size will look smaller to us. And in a closed universe, it turns out light rays converge as you go back in time, so that same lump will look bigger. So all we have to do is take a picture of that surface and ask how big are the lumps. Are they half a degree, 1 degree, or 2 degrees? And we'll measure the geometry of the universe. And that's what we've been able to do in the last decade or so. This was the first experiment that allowed us to do it. It's called the boomerang experiment. It's a balloon and a microwave radiometer, because this radiation is in the microwave band. And this balloon took the radiometer way above the Earth, because the Earth is hot, and it was designed to look at a small region of the sky, and this balloon went around the world, which is easy to do in Antarctica. You do in the South Pole, you just do this. It wasn't quite the South Pole, it was McMurdo, and therefore it took about 2 weeks to go around Antarctica and came back to where it began, which is one of the reasons why it was called the boomerang experiment. And this is the image it took. I've superimposed it on the original picture. This is false color, of course, because these are microwaves. But this is the baby universe. These are the primordial lumps created at the beginning of time that would later collapse to form galaxies and stars and planets and aliens and everything else. But the big question is, how big are they? And to do that, we can create universes on a computer. Here's a different false color image of the same region. And I can create universes on a computer randomly, closed universes, flat universes, or open universes. And I can compare how big the lumps, the 100,000 light year across lumps in those simulated universes would be compared to what we see. And in a closed universe, 100,000 light year across lumps look that big. But that's bigger than these lumps. And in an open universe, 100,000 light year across lumps look about that big. But that's smaller than these lumps. But just like Goldilocks, in a flat universe, it's just right. And we now know to an accuracy of better than 1% that our universe is indeed flat. Now, we can pat ourselves on the back. Except there's a problem, because I just showed you when we weigh the universe, we only get 30% of the amount of stuff needed to make the universe flat. There's a problem. Well, if you weigh the universe and there's only 30% of the amount of stuff around galaxies and clusters to make the universe flat, where could the rest of the energy be? Well, it must be where the galaxies aren't. But what is where the galaxies aren't? Nothing. Let's go back to Einstein. He wanted to get rid of this cosmological term, and he get rid of it, but it's kind of like trying to get the toothpaste back in the tube after you've gotten it out. If he hadn't introduced it, someone else would have, because nowadays we think of this term very differently. Because of the miracle of modern mathematics, we can rewrite this equation. This is a small step for a mathematician, but a giant leap for a physicist. Not because it's that hard to take this term and put it over here, but in physics, equations actually mean something. And so this term, remember, on this side of the equation, describes geometry. But when we put it on this side of the equation, it acts like a new kind of energy. Now, what kind of energy could produce such a term? It turns out there's only one kind of energy that can produce such a term. The energy of nothing. And by nothing, I don't mean nothing, I mean nothing. I mean if you take a region of space and get rid of all the gas and radiation, everything, so there's nothing there. If that region of space weighs something, then it will produce such a term. Now that's insane. Nothing can't weigh anything. If you ask a 4-year-old how much energy is there in nothing, they'll tell you nothing. But that 4-year-old hasn't taken quantum mechanics and special relativity. And if you put the two of them together, you find that in fact nothing ain't nothing anymore. Nothing is a boiling, bubbling brew of virtual particles popping in and out of existence in a time scale so short that we can't measure them directly, called virtual particles. Now that sounds like philosophy, because it sounds like, or theology, which is worse, because it sounds like counting angels on the head of a pin. If you can't measure it, then what's the point of talking about it? Well, you can't measure these virtual particles directly, but it turns out we can measure their effects indirectly. And this picture I'm showing you is an actual animation of a calculation of what the space inside of a proton looks like. It's a calculation that required a lot of modern physics to be performed. In fact, it was shown at the Nobel Prize ceremonies in 2004 by the people who developed the theory of how to do the calculations. And the amazing thing is, you may have heard, if you've taken physics, that protons are made of these particles called quarks. But it turns out the quarks don't account for most of the mass of the proton. They only account for 10% of the mass. 90% of the mass of the proton comes from these virtual particles and fields that are popping in and out of existence. And if it weren't for the case, your protons and neutrons, all the mass of your body is due to virtual particles. You wouldn't be here if they didn't exist. So we know they exist. Now, if we can calculate the mass of the elementary particles and the energy that's contributed by the energy of empty space, of these virtual particles to protons, we can try and calculate the contribution of these virtual particles to really empty space where there aren't any protons. And when we do that, we come up with not the best prediction of all of physics, but the worst. We calculate that the energy of empty space should be roughly a gazillion times the energy of everything we see. 120 orders of magnitude more than the energy of all galaxies and everything else. Now that's so crazy, because if it was the case, the universe would be expanding so fast, none of us would be here. So it really is the worst prediction in all of physics. We know it's wrong by at least 120 orders of magnitude. And it's been around since I was a graduate student. Because it's such a big problem, we never talked about it. But we knew the answer. I told you, theorists always know the answer. It has to be zero. Because there's no way to get rid of this big number and leave something non-zero in the 121st decimal place. But zero is really neat. You can make mathematical symmetries that cause things to exactly cancel. So we all knew that the number was zero, and there'd be some new symmetry of nature, and one day we'd understand it. But the thing about cosmology and science is, I repeat, it doesn't matter what we want or what we think is sensible. We have to find out what's sensible by asking the universe rather than the other way around. And cosmology is an empirical science, so as much as we knew the answer was zero, we should go out and look for it. Now, what would be the impact if the energy of empty space wasn't zero? Well, I remind you, it produces a cosmological term, and that's gravitationally repulsive. So if we measure the expansion rate of the universe, this Hubble curve, and look out at very far distances, well, a sensible universe, the curve should bend downward as the universe is decelerating. But if there was energy of empty space, it should turn upward. In 1998, two groups of astronomers who didn't know what the hell they were doing, well, they knew what they were doing, but they didn't quite know why, went out and measured these type 1a supernovae at large distances and determined that this was the cover of Science magazine. It doesn't look like much, but it is a lot. To interpret it, I want to just draw a straight line. Here's the Hubble curve I showed you earlier. A straight line, just a perfectly straight line through that data set, and bring the whole thing down so the straight line is horizontal. If the universe was decelerating as they expected it to be, and they wanted to measure the rate at which it was slowing down, then these distant supernovae would fall along this curve. But they don't. They don't even fall on the straight line. They go above the curve. Now, there's only two ways that could be the case. One, the data could be wrong, often is. Or two, the universe is accelerating. It's speeding up. And if just for fun I ask how much energy do I have to add to empty space to make the universe speed up this much, I get exactly what we were missing. We get 70% of the energy needed in a flat universe, and that's exactly what we were missing. So everything holds together with this cockamamie universe. This is the universe in which we live, in which nothing is almost everything. Almost everything. 70% of the energy of the universe resides in the empty space, and as I'll point out, we don't have the slightest idea why it's there. If anyone comes here and tells you they do, they're lying, especially if they're string theorists. Its existence is probably tied to the nature of space and time and the origin of our universe, and it will determine our future, as I'll describe near the end. But it really emphasizes yet another fact, that you are more insignificant than you thought you were a few minutes ago. Because now, we know that 70% of the energy of the universe resides in empty space, 30% resides in dark matter, and something like 1% resides in everything we can see. 99% of the universe is other stuff. We really are completely insignificant. Now, it's changed everything, and I want to talk a little bit about how it's changed everything. I want to talk about this. Remember, I told you I got into this field because I wanted to learn how the universe would end, and it turned out to be a misplaced notion. Because it turns out it's easy to determine how the universe will end. We can do it as we would in an introductory physics course if I had a coin, but I don't have one, so it doesn't matter. If I threw an imaginary coin up, it would come back down. If I threw it harder, it would go up higher, take longer to come back down. If there was no ceiling, if I threw it up really hard, it wouldn't come down at all. Now, in kindergarten, we teach kids how to calculate this. Okay, you'll remember back to kindergarten. It turns out we can say that energy of that coin has two pieces, a positive piece, something called the kinetic energy, and a negative piece, something called the potential energy. And it turns out it's just bookkeeping. If these two things add up and the total energy is greater than zero, the coin will escape. If it's less than zero, the coin will come back down to Earth. That means if this term is bigger than that term, the coin will escape, so you have to get the speed fast enough to escape. 11 kilometers per second from the Earth's surface. And if it's less than that, then the negative term beats the positive term. And if it's exactly zero, then the coin will go out to infinity and just escape, slowing down and never quite stopping. Well, it turns out, let's look at our universe. Remember this region of the universe, we're at the center, and there's some galaxies moving away from us. If this region is small compared to the size of the universe, Newton works. And if the universe is the same everywhere, I can determine the future of the universe just by looking at a single galaxy. Whatever happens to that galaxy will happen to all galaxies. And to determine whether it's going to stop and come back again, I just do the same calculation I did for the coin. So I calculate the positive piece. Well, the positive piece comes from its velocity, but Mr. Hubble told me its velocity. The negative piece comes from the total amount of mass, the gravitational attraction of all the stuff in there, including the dark matter. And if B over A is bigger than 1, the universe will collapse. If B over A is less than 1, the universe will expand forever. And it turns out, amazingly, that this quantity B over A is nothing other than omega. The quantity I told you before. And we now know we live in a flat universe where omega is 1. What does that mean? That means B is exactly equal to A. What does that mean? That means the negative energy is equal to the positive energy. What does that mean? It means the total energy of the universe is 0. Now, if you were going to make a universe from nothing, what total energy would you give it? One of the big problems of people who suggest something can't come from nothing is that you can't get, they pretend they're physicists. They say,
You can't get energy from nothing. One of the great things about the universe is, because of gravity, you don't need energy. So I want to talk about some of the implications. Now that you're wise enough to know the data, let's talk about the implications. And I don't say that sarcastically, because it always amazes me that people argue ad nauseum over centuries about this issue without ever asking what the actual universe looks like. So, now we know a flat universe is the only one where the gravitational energy of every object is on average precisely equal to 0. It didn't have to turn out this way. But that's one of the reasons we thought the universe was flat. It didn't have to turn out that way, but it did. It could have been falsified. So, let me now end in the last few minutes talking about how you can get something from nothing and the implications of this. First of all, nothing number one. What is the nothing of the Bible or the ancient philosophers? You see, when I talked about this, and since the book has come out and even before, I talk about nothing, and what I've discovered, of course, is that the philosophers and theologians don't really have a definition of nothing. So the nothing of the Bible would be an eternal void, empty and eternal and dark. That's a pretty good, that's the nothing of Plato and Aristotle and maybe the Bible. Well, that nothing is clearly not nothing. Because that nothing can create something. Because in fact, nothing is unstable to forming something. Because nothing, empty space, produces virtual particles all the time that pop in and out of existence in a time scale so short you can't measure them. Well, that's not stuff. There's nothing there. But when you put gravity into the mix, because gravity allows negative energies, you can create particles, and if their gravitational attraction is strong enough, then their total energy is precisely 0. And then quantum mechanics will tell you that those things must be created, because quantum fluctuations are happening all the time. And if there's a state of particles that exists with 0 total energy, if you wait long enough, it will have to come into existence. So the reason there's something from nothing in that case is simply that nothing is unstable. These particles will eventually, in a strong gravitational field, produce stuff. So if you have empty space and you wait long enough, that empty space will always fill up with stuff. Nothing is unstable. And that's because of the fact that the wonderful miracle, if you wish, of general relativity, or of gravity in general, is that gravitational energy can be negative. And that means there's no contradiction in making stuff come from nothing. There's no violations of energy, no magic, and no need, most importantly, for anyone to intervene. You don't need supernatural creation. Nature will always create something from nothing if you have empty space. Now, once I say that, I'm told by my theological colleagues or philosophers that, well, that's not really nothing. Of course, it was nothing for them. It was good enough nothing until I told them something could come from it. But that's not nothing because you got space. It may be empty, but where did the space come from? Well, it turns out that once you apply gravity and quantum mechanics to gravity, then space itself becomes a quantum object. And if you have a quantum gravitational theory, then you will create space where there was none before. Just like in theories of the rest of particle physics, you create particles within space. Once you allow space itself to be a quantum object, you will create universes where there were none before. Space will spontaneously arise. Now, such mini-universes will spontaneously arise and disappear in a time scale so short that you can't measure them unless their total energy is 0. So the only universe that can survive for a long time is the universe with total energy 0. Now, it may all sound simple because I just told you our universe has 0 total energy. Well, I lied. I didn't quite lie. Our universe has 0 gravitational energy. But Einstein told us on top of gravitational energy there's rest mass. And it turns out we can't quite do the calculation for any universe but a closed universe right now. We don't know how to do the calculation. But we do know that a closed universe has 0 total energy. So, with impunity, closed universes should be popping in and out of existence all the time. Now, most of them, because where quantum mechanics and gravity becomes important is a scale so small we can't even see it. These universes will pop into existence and collapse at a time scale of something like a billionth of 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 a second. Now, as many of you can tell, have been sitting here, we've been in this lecture hall longer than that. It seems like an eternity. So, how does this explain our universe? Well, it turns out the only universe, our universe is flat, not closed. I just told you that. But it turns out the only way to make a closed universe last for a long time is to puff it up at early times. It turns out, in our theories of particle physics, that's exactly what we predict. We predict that there's this phenomenon called inflation that should have caused our universe to puff up by a huge amount in the first fraction of a second. Moreover, that puffing up, if it's due to quantum mechanics, would produce little lumps. Those lumps are exactly the kind of lumps we observe in the microwave background. So all of the stuff that forms our galaxies and us is really due to quantum mechanics. We are the remnants of quantum mechanical fluctuations. But if you take a closed universe and puff it up, it's like blowing a balloon up. A closed universe that gets bigger and bigger and bigger by that phenomena will look more and more flat. So the only closed universe that can live long enough to have people in it, who take at least 4.5 billion years to evolve, and I can still say evolve, is a closed universe that's large enough to look flat. So the only universe that could have been created from nothing is a flat universe. And that's, again, precisely what we see. So, we don't need particles. Space will make particles. The second thing I've told you is you don't need space. Space itself will come into existence. Now, when I say that, the philosophers and theologians tell me, well, that's not nothing. Because, well, you don't have the particles, and you don't have the space, but you have the laws of physics. Who created the laws? That's where you need God. Well, stay tuned. The last thing I want to show you is something truly remarkable and plausible, is that even the laws of physics themselves may be an accident, may have come into existence when the universe came into existence. And the reason for that is this crazy discovery about the energy of empty space. This is the last sort of complicated thing I'm going to show you. It's not that complicated. It's a graph. It's a brief history of time. This is the density of matter as the universe expands. It goes down. This is the density of energy in empty space. It's constant. It doesn't change because there's nothing to get diluted. We live today here when the energy of empty space is 3 times the energy of matter. But when you look at this picture, something strange you should know something extremely strange. We are living in the only time in the history of the universe when these two quantities are the same, within a factor of 3. At all earlier times, the energy of matter was much bigger than the energy of empty space. At all late times, the energy of empty space was much bigger than the energy of matter. Why should we live at such a special time? 13.7 billion years after the Big Bang. Copernicus told us it's not supposed to be that way. There's nothing special about where we live or the time we live. But why is this such a special time? This has driven physicists crazy. Literally, as you'll see. The answer that's been proposed is that galaxies exist. Why is that an answer? Well, let's imagine the energy of empty space was a different number, say 50 times bigger. So it wasn't that, it was there. Well, these two curves are crossed at a different time, not today, but this time. What time is this? This is the time galaxies first formed. Now, the energy of empty space is gravitationally repulsive. So if it dominated the expansion of the universe before galaxies formed, it would push apart matter before they could collapse. You wouldn't have galaxies. And if you don't have galaxies, well, maybe that's telling us something. And this has produced something I call anthropic mania. If there are many different universes, and in each universe the energy of empty space is different, then only in those in which it's not much greater than what we measure today will galaxies form. And only then will stars and planets form, and only then will astronomers form. So the universe is the way it is because astronomers are here to measure it. Think about that. It sounds ridiculous. It sounds almost theological. It's not. It's kind of, in fact, it's perfect to talk about at Darwin Week because it's kind of a cosmic natural selection. We would not expect ourselves to find ourselves living in a universe in which we couldn't live. In fact, the opposite would be quite fantastic. So it is just like bees can see the colors of flowers, not because they're designed to do it, but because if they couldn't, they wouldn't be able to get the nectar and reproduce and pass their genes on. We it's not too surprising that we find ourselves in the conditions of a universe that, in fact, allow galaxies to form and planets and stars and people. So this is this possibility, of course, is repugnant to me, in a way, because it suggests if this is really true, then this fundamental quantity, the energy of empty space, is not a fundamental quantity in nature, it's an accident. It's an environmental accident. But it may be true. But, particle physicists are way ahead of cosmologists, because cosmologists don't understand one number. But particle physicists haven't understood many more numbers for much longer. We don't know why gravity is the weakest force in nature. We don't know why the proton's 2,000 times heavier than the electron. We don't know why there are 3 generations of elementary particles. So, there's all sorts of questions, and particle physicists have jumped on this. They said, maybe everything's an accident. Maybe every fundamental quantity in nature is not fundamental, but an accident. And they're all different in different universes, and in that case, you don't need a theory of everything, you need a theory of anything. We have such a theory, it's called string theory. Let me tell you string theory. Or one case summary of string theory. So one guy says to another, I just had an awesome idea. Suppose all matter and energy is made of tiny vibrating strings. And the second guy says, okay, what would that imply? First guy says, I don't know. That's the history of string theory in the last 40 years. My friend Brian Green doesn't like it when I point that out, but he's coming to accept it. But string theory, one of the big downers, was that everyone thought string theory would give you a theory of everything. A unique theory that would describe why the universe was the way it was. But the problem is string theory actually predicts 11 dimensions, or 10 or 11 dimensions, and we don't see 10 or 11 dimensions. We don't play baseball in 10 or 11 dimensions. So where did all those extra dimensions go? Well, the conventional wisdom is that they curl up at a scale so small you can't see them. They're so small that no microscopes can't even resolve them. But it turns out every different way you compactify these extra dimensions produces a different 4-dimensional universe. And string theory, it's argued, predicts maybe 10 to the 500 different universes, each of which would have different laws of physics. And then you're guaranteed to find one that looks like ours. Now, is that science? I mean, if you can explain any possible universe you see, is that really science? Because you can't falsify it. Then, is it science? Well, that's a good question. It may not be science anymore. But it may be true. But if it is true, then all the laws of physics in each of these universes arise as the universe forms. There are no laws of physics. They're all accidents. And in that case, in this case of this multiverse, the multiverse, if you wish, plays the role of the prime mover or God. The argument being that, okay, our universe had a beginning. What caused our beginning? Well, it turns out you don't need really causes in physics, I would argue. But if you like a cause, you could argue that the multiverse exists eternally, just as a prime mover, in the case of Aristotle, would have existed. Or, as for some people, God would exist. But the huge difference between God and the multiverse is is well motivated. I've often, when I debated with theologians, they say you invent this because you're atheists. It's not true. We didn't invent the multiverse for any philosophical reason or anything we didn't like. We've been driven to it by measurements of nature. And as I say once again, what we like or don't like doesn't matter. I don't even like the multiverse, but it may be true. And if it is, then it seems to me that's the last bastion of nothingness. Because we don't need particles, we don't need space, and we don't need laws. So, the last thing in deference, I know I've gone on 10 minutes too long and I want to spend only 3 or 4 minutes on this, but I want to do this in deference to a very good friend of mine who died recently, Christopher Hitchens, who, when I was explaining this to him, pointed out to me that nothingness is heading straight towards us. Because, remember, I told you that the energy of empty space determines our future. And our future is miserable. The 2 lessons I want you to get from this lecture are, 1, you are insignificant, and 2, the future is miserable. Because if we think what's going to happen in the far future, it's kind of poetic. 100 years ago, as I described to you, we thought we lived in this static universe with a single galaxy. What's going to happen in the far future, not on our planet, but on planets or on stars hundreds of billions of years from now in our galaxy? What will those astronomers who evolved see? Well, because the universe is accelerating, all of the galaxies we now see will be moving away faster than the speed of light. That's allowed in general relativity, it turns out. But once that's the case, they'll become invisible. And observers in the far future will think they live in the universe we thought we lived in 100 years ago. They will observe a single galaxy surrounded by an eternal empty space, and all of the evidence of the Big Bang will have disappeared. And then that galaxy will eventually collapse to a black hole, which will evaporate, and we will be left with a cold, dark, empty universe. And in that case, because the rest of the universe will disappear before our very eyes, the simple answer to the question, why is there something rather than nothing, in that case would simply be, well, just wait, there won't be for long. Because we have this incredible conceit, just like we do in biology, that we are the pinnacle of evolution. Well, we're a point in evolution. And we also have this conceit that the universe was created for us, and it ain't going to change. But in the far future, the universe will be vastly different. All remnants of us and all matter will go away, and the universe will revert to a state of nothing. So the answer to the question, why is there something rather than nothing, becomes trivial. If there were nothing, you wouldn't be there to ask the question. That's all. I think I'm going to skip Einstein, as much as I like Einstein. Yeah, I think I'll skip this, even though it's profound, but I've gone on 10 minutes too long. Well, actually, let me just go back here. I like the last statement, and if you want to understand it, you have to read the last part of my book. But the key point is, what this suggests, I want to point out that what I've argued is not the way the universe must be. I didn't prove to you the universe was created from nothing. But what I've shown you is that it's plausible. In fact, not only is it plausible, but all the evidence is consistent. I find that remarkable, and it is and Richard Dawkins wrote a very nice afterword for my book, comparing it to the origin of the species, which was quite nice of him. But without that conceit, the point is it's very similar to what Darwin did. Before Darwin demonstrated that the diversity of life on Earth can arise by natural causes, it was a miracle. Now Darwin didn't prove it. He didn't know about genetics. He didn't know about DNA. But he showed it was completely plausible, and all the evidence was consistent with that. What we have learned in cosmology in the last 100 years has told us that the same thing is true for the universe. I can't prove to you it came from nothing, but I can show you that it's plausible. And moreover, if I ask what the characteristics of the universe that came from nothing are, they're completely consistent with what we can see. And for that reason, among others, God is completely unnecessary, or at best, redundant. And to me, I find that very satisfying. So, science has demonstrated that the universe from nothing is not only plausible, but likely. And the key thing I wanted to stress is what I said at the beginning. What we mean by something and nothing has completely changed. The very question doesn't mean the same thing at all. And when people say to me, well, you're not talking about the classical nothing of philosophers, I say, who cares? That classical nothing is irrelevant. Because it doesn't relate to the universe that we actually live in. So don't talk to me about it. The question, why is there something rather than nothing, is not the interesting question. The interesting question is, how did the universe evolve, and how can we find out? Those are the questions where there are progress. And we've made incredible progress, and we should celebrate that progress instead of being afraid of it. So, the future, indeed, I've told you, will be lonely and ignorant, but will be dominant. And those of us who live in the United States are used to that. Thank you very much. I'm really moved by that. I appreciate that. Now, what I'd like to do... I'll still talk for a second. You could probably talk too. Okay. I don't know if you want, but I know that people have bladders and other things to do, so I don't want to keep you here too long, but I am willing to answer one or two questions in public, and then at the book signing or later on this evening, I'm happy to answer questions all night long. It doesn't matter. But I will take a few. Is that okay?
Yeah, I was just going to say, we have Q&A, and then there's, like you said, books. There are shirts for sale at Malati. And because we're insignificant and the future will be miserable, we're going to Beck's. Anyone who'd like to join is more than welcome.
So, and I'll be there. Okay, so any questions? Any burning questions? Any interesting questions about anything while we're in public? Anyone brave? There's someone, yes. Quantum foam, John Wheeler called the fact that space-time becomes quantum mechanical as quantum foam, yeah. It's just a word, though. We don't really have a quantum theory of gravity yet, so we can't do the calculations. But he argued that, indeed, if space is quantum mechanical, then there'll be fluctuations creating little baby universes and foam, just like sea foam. And Wheeler was also the person who coined the term black hole for black holes, and he had a good way with words. Because in Russia, it's actually interesting. Black holes are called frozen stars. You never see movies in Russian about frozen stars because it's not as sexy as black holes. But anyway, it's a word, but we don't yet have a theory yet for what the space-time foam looks like, but we know that if quantum mechanics applies to space, it must be pretty wild on small scales. Any other questions? Yes.
So what's with the particle moving faster than the speed of light?
Okay, I always get asked that.
Oh yeah.
So unfortunately, these experimenters discovered that claimed they measured these particles called neutrinos coming from the Large Hadron Collider in Geneva. They measured them in Italy, and they claimed that they arrived 60 nanoseconds, 60 billionths of a second faster than they should have if they were traveling at the speed of light. And that, of course, is astounding. It's also wrong. It's wrong for many reasons. We don't know why yet. But it's wrong for a number of reasons. First of all, it actually does conflict with other experiments that I won't go into. But there's really good theoretical reasons to believe it's wrong. And in fact, the speed of light being in that sense an ultimate speed limit is the foundation of all of particle physics, all the stuff we build accelerators on, and we know it works. But on the BBC recently, I gave the ultimate argument for why we know it's wrong. Why I know it's wrong. That is, nothing ever arrives in Italy early. In any case, it's probably whatever the experience. It's like UFO. People come with one of my other hats, because I have too many hats. I've debated UFO people in the old days, and they, and the point is, I try to tell them, look, I can't say that I wasn't there, but I can tell you that any explanation of what you saw, no matter how wild, is more plausible than a spacecraft coming from another star and abducting psychiatric patients of Harvard psychiatrists. What I would say for the neutrino experiment is there's lots of mundane explanations. You only need 20 extra meters of cable in the experiment that's not accounted for to account for 60 nanoseconds. There's lots of possibilities. And they're all mundane. Some of them are quite wild. But any one of them is more plausible than the likelihood that the neutrinos are going faster than light. It's not going to happen. One last question, if there is one. Oh, yes.
Because a question on semantics. Okay, we're having Darwin here. We're talking about the theory of evolution. Okay, as you sit in here, it's
we're talking
astounding.
About evolution is a theory, it's a fact.
Of evidence that that's related to that. Now we talk about string theory. Isn't that more of a hypothesis?
No, absolutely. I've said it. In fact, string, as I've often said, and again, I used to get Brian Greene got furious when I said, but now he agrees with me on this one. String theory, saying string theory is a theory is an offense to evolution. Because it suggests that a theory is just a hypothesis. And an evolution, if you want to call it a theory, is a theory in the same sense that quantum theory is a theory, or gravitational theory is a theory. A theory in science is something that's been tested by experiment over and over again and validated by experiment. And string theory is absolutely not that. So it is a misnomer, and it's an appropriate term. And we should be, and it is unfortunate, because I have been often in debates a while ago, people say, yeah, but you say this but string theory is like religion, and science is like religion, because it's just a theory, and so is evolution just a theory. And you're absolutely right, we should be very, very careful in distinguishing what theories are versus scientific theories versus hypotheses. String theory has not been tested, it hasn't made any predictions, really, to be tested. To be fair, it really hasn't. But Darwin's evolution has been tested more than any other scientific theory of the last 150 years. Quantum mechanics has been tested, and all of these things, they survived the test of experiment, which is why we use them, not because we want to be right. In fact, as I pointed out recently on TV, I think that the two greatest states that a theoretical physicist wants to be in are either wrong or confused. Because then you know you're going to learn something. And it's not as if we all have this little enclave where we have PhDs and we have these secret handshakes. Don't tell anyone. Evolution is not right. Because